Hello and welcome to the Civil Black Box YouTube channel. If you're new to this channel, do consider subscribing and hitting that notification bell. Also, I have a free ebook for you to download, which will show you the step-by-step method of starting your own structural consultancy business. The link to that book is in the description below. Go ahead and download it right now. With that said, let's move on with the video. In this video, we'll be talking about what a great structure really means. What are the key properties of a great structure? Now, the structures I'm about to show you may not be something which you may have seen or you may have heard. There may be some of these which are common and usually heard of, but just bear in mind that my definition of a great structure really revolves around three key aspects which we will look for at the end of this video. But in general, assess these structures based upon when they were created and what kind of technology was available at that time. And that is basically what defines something great. Having a great technology at any point can let you do great things. But to build something out of the ordinary, out of the box, takes a great deal of zest, mind, and courage. So we will be talking about great structure in those terms. Now, this is just to let you know what could be done and what was done, probably without using any softwares, without using any analytical means, and to give you a brief as to what you will be able to do with all the computing power available with you. So let's get into it. The first structure we'll be talking about is the Brooklyn Bridge. Now again, imagine this bridge being built in 1869, or at least it started in 1869. So this is a suspension or a cable stay hybrid bridge. I'll show you the bridge and then we'll talk about it. So this is the Brooklyn Bridge. Just see what is going on. So these are the cables which are actually carrying the weight. In fact, these are the members which are actually carrying the weight. And in fact, this is the truss which is carrying the weight. So all in all, the truss is moving the load upwards, which is moving the load to this column, and ultimately this load is moving down. And this was built at a time when all the calculations were to be done with hand. This is just another view of the same Brooklyn Bridge. So these are the cables and the suspenders which are actually taking up loads. So these are all in tension. They are taking in the loads. They are transferring the loads down to these supports or columns in this case, and ultimately taking down to the foundation. Then we have another bridge, which was the Firth of Forth Bridge. Now this is a great example in the history of bridge building. Again, mind you, this was built in 1882 after one of the nearby bridge fell. So after the collapse of one of the nearby bridges, this bridge was supposed to be built as a symbol of strength, and that is what was made. You can see the extraordinary amount of steel that has been put into it, the extraordinary weight. This, by the way, is called a cantilever bridge, and we'll talk about these in a little bit, but you can imagine this portion being the cantilever and this portion being the cantilever, and this is holding this small portion of the bridge as a pin joint. So this is a pin joint right here, and it is holding the bridge. Now this was built at a time when public demand for a stable structure was a bit too high. Since one of the nearby bridges collapsed, as I said, this bridge was to be built to pacify the minds of the public, and so it was done. This has excessive weights in steel, and in fact some would say that this was one of the most uneconomical bridges. But mind you, this was not its function at that time. The function was to tell the public that it was safe to go along across bridges again, and that is what it did. Then we have one of the first bridges which had the longest span at that time. This is the Akashi Kayoko Bridge, and you can see this is again a suspended bridge, a cable suspended bridge, which is taking up the loads in using this main cable, which is in the parabolic shape, and with these suspenders which are always in tension. And then we have a truss right here. So I'll take you through one of these bridges in a little bit, but just imagine the scope of work here. Then we have the CN Tower, which remained the highest tower for a long time. This was built in Toronto, which was later taken over by Burj Khalifa in Dubai, which stands at an astounding 828 meters. Now, this is approximately a kilometer above ground. Imagine that, going vertically 1 kilometers. So this is still the tallest building in the entire world. And just to keep things in perspective, when you're trying to see a structure something as huge as 828 meters, you may think that something different would have gone into creating this structure, or at least in the designing part of it. But you have to imagine or you have to understand this very simple logic, that all in all, what is being essentially done is every member. So if I just take out this member from here, every member which is there has to be designed to sustain loads. That's all. If this member or any member and all of the members are able to sustain loads, this is going to be a stable structure. And that is what essentially we are going to do. It is as simple as that. And we'll talk about that. But you have to not see this as an 828 meter building, but a building which has so many parts of members, or so many members which are able to sustain whatever loads are being put on it. And that's all there is to structural design. Let's move on to another famous, or rather iconic tower, which is called the Eiffel Tower. Again, this was built in 1887, ended in 1889, stood at an astounding 324 meters at that time, you can imagine, and still is one of the most legendary buildings in the entire world. With the intricate design of all the members which are connected, you can see the amount of calculations that would have gone into it. And even now that we are disposed with such great softwares, just the mere thought of recreating this would be a challenge in itself. Imagine them doing it using manual calculations. Then we have a strange building called the Guggenheim Museum. Now, this won't in general look like much to do with structures, but this has been created as a weird architectural feat. Now, behind every architecture, or behind every architectural element rather, is a structural engineer standing and supporting that architecture. And that is what is shown in this structure. The weird angles, the weird cantilevers, and the weird shapes are being internally supported by some structures, and these have been created by a structural engineer. However, when people come to this Guggenheim Museum, they're only concerned about the architecture. We are the silent heroes, and I love to believe that. And as a silent hero, we have to work silently and keep supporting whatever feats or whatever ideas are being floated upon us. This is another view of the Guggenheim structure. Next is the famous Taj Mahal. Now again, just keep in mind the year of construction, 1632. And this feat was made in 1600s. Imagine the calculations that would have gone, however empirical, however simplified, to create a structure of this magnitude at the 1600s is an astounding feat, and it deserves to be in the wonders of the world. So what makes these structures great? Now, in my opinion, any structure has to be great if it has three key properties, and none of these properties can work in isolation. The first is the function. A function is the aesthetics of a building. It's the functional use of the building, and in some cases the public demand. When we are talking about structures like Taj Mahal or the Guggenheim Museum, we are talking about the aesthetics, because that is what was important then, to create it in a beautiful way. When it comes to bridges, the most important case or use case is the functional use. And when sometimes it so happens, as I showed you in the Firth of Forth bridge, that the public demand was the important thing. So out of these three parameters, function plays an important role in some of these and not so important in the others. The second key aspect of it is the structure itself. Now, a structure would be great if it has a great height demand, maybe something like the Burj Khalifa, or a length demand, maybe like the Brooklyn Bridge at the time. Not only this, a great structure is something which is made with the available tech. Building something in 1600s is much more different than building something in the 21st century with all the technical advantages we have. The third key aspect of it is the economy. And this perhaps becomes one of the most important parameters in the present situation, where we have to create the lightest structures and the most cost-effective structures. So these are the three properties which actually define what a great structure is. First is the function, the second is the economy, and the third is the structural stability. However, you have to understand one simple thing, that we can play along or we can play with these two parameters. So we have these two parameters of function and economy at our disposal. We can end up altering a little bit of functionality. So if an architect has given us a weird design which cannot be done, we can alter that, and the funding can be increased based upon the public demand. But what can not be done but rather must be done is the structural safety. Just bear in mind, we as structural engineers fall in this criteria where there is no option of a can be. We are always in the must do zone, and this is both a responsibility and a kind of compliment, which you at least you must have to see it that way. This is where we need great structural consultants to create a structure which is not only fully functional, which is not only completely safe, but which is also having the minimum cost. And if I were to define a structural engineer, a good structural consultant, I would define it in this single page. I will give you this snapshot as a pinup. You should always look at it. You have to provide whatever functionality a client or an architect wants of you. You have to make the structure safe. You have to make it cost the least. But bear in mind, safety of the structure is a must. You can increase or decrease functionality. You can increase or decrease cost. But this is a must. There should never be any compromise. Now, that being said, we must keep in mind to never over design. The structure should be made safe at a minimum cost. And that is why I like this diagram. It gives you your core responsibility. Being a good structural consultant, you must have these three features. Whatever the architect gives you, you have to comply to it fully. No holds barred. You have to minimize the economy as much as you possibly can without compromising the safety. So safety is your number one priority. Full functionality is your number second priority. And keeping the cost minimum is your number third priority. That doesn't mean that you have to not keep it at a minimum, because that is what a normal client would pay you for, to reduce his cost. So I'll give you this pinup, of course, without the scribble. Print it out, keep it in front of you always, because this is what will define you. Of course, this won't be your zone of working, but you have to ultimately work with a client or with an architect that the client has hired, and you have to go through the functionality and make it happen. So if someone gives you a hall of weird dimensions of say 20 meters by 40 meters without any columns in between, you have to make that happen. How? That is your part. At a minimum cost, that is your part. So I'll end with this. You have to create a safe structure with full functionality at a minimum cost. And this is what is the roles and responsibility of a good structural consultant. If you like the video, do not forget to hit that like button. It really helps with the YouTube algorithm. And once again, if you haven't already downloaded my free ebook on how to start your own structural consultancy business using a simple 12-step formula, do so now. The link to that book is in the description below. Thank you for watching, and check out the other videos on this channel right now.